This is a video covering programming of my relay computer, and it forms part of a 2020 update series of videos, and this is a fourth in the series. So far we've covered off the architecture of the relay computer, the instruction set it uses, an assembly language which makes it easier to program the computer, and then we have this video. Later on we'll do a tour of the computer and then finish off with a demo of a program running on that computer. So if we cast our minds back to the first video in the series, that's where we found the architecture diagram, and that's shown on the left there. And in the video following that, we looked at the set of opcodes that allow us to control the computer. Now, as we noted, it's not straightforward to program the computer in a load of ones and zeros. Something the computer understands well, but it's very hard for us to work with that. And so in the third video, we introduced our assembly mnemonics. And this gives us a much easier way of coding the computer in a way that's easy for us to remember, but all of these have a direct one-to-one relationship with an opcode. So what we're going to do in this video is start with a programming task, and then we're going to take that and build an assembly program out of it. Once we've got that, we'll convert it into a list of opcodes, effectively hand assembling it, and then we can try running the program on the relay computer simulator. So what is the programming task then? Well, actually, this has come up in comments on previous videos, and something that's been mentioned as something you'd like to see is calculating the Fibonacci numbers on the relay computer. And now actually this works out as quite a nice task, because it's going to need an element of branching, which is great because the computer can now do that, but it's also a nice simple example to understand as well, so that's the one we'll go with. If you're not familiar with this series, you can see the numbers here. So we start with 0, 1, 1, and then each number goes on from there. Now, if you've not spotted the pattern here, each number is the sum of the previous two numbers. Now, we can write that as a formula as follows. So starting with 0 and the next term being 1, any term can be found out by adding the previous term and the term before that together. Now, Fibonacci numbers are pretty cool, and if you've not played with them much or you are new to them, definitely have a look at this link below, because these numbers appear all over the place. They appear in nature, they sound quite nice in music. If you're in the UK, your piece of A4 is also tightly related to these numbers. So if you want a quick diversion and interesting read, this is a good place to start. But anyway, this is the programming task we're going to set ourselves for this video. Okay then, so let's crack on with this programming task then. So you can see in the bottom left here then, we've got our challenge to create the Fibonacci numbers on the relay computer. And over on the right there, I've got the usual architecture diagram, which will just help us when making this program specifically work on the relay computer. So I guess a good place to start would be to look at that general formula. So let's just quickly write it up here in our text document to start off with. So effectively we have f0 will be 0, f1 is 1, and then from that point onwards fn is always fn minus 1 plus fn minus 2, where n is greater than 1. So that's a general formula, but how would that look as a computer program? So what we need to do is actually write this as a series of instructions, a series of tasks that need to be performed. And at the moment that last one doesn't make much sense. So let's find another way of writing this. So we could actually say that we're going to call this A, and we're going to call this B, which is fine. So then C, in the first instance, would be A plus B. And that gives us our very first result of 1. But what we need to do after that is we then need to reassign what A and B are. So we could say, well, A now becomes 1, and B now becomes the result of that addition, and then we can go around for another iteration. So we could then say, well, let's do all this. So what we can do then is just iterate on this forever, because the sequence just carries on going all the way to infinity, so let's do the same here for the example. And then what we've created here basically is a pseudo code. So this is not any language in particular, it's just a made-up language, but it's enough for us to get the logic flow of this. And what we can do then is we can sort of try this out and see if we're hitting the right markers. So if we said, let's do A, B and C, we know that to begin with, we start off with that, and C will then be 1. We then set A to B, B to C, and then C is then 2, and the pattern follows. So that becomes 1, that becomes 2, and that becomes 3, and that looks like that's working absolutely fine. So effectively, that is a pseudo program for calculating the Fibonacci numbers. Right, okay, so let's see if we can make this specific to our computer. So straight away, if we imagine that these letters we've used are the registers, we can see a problem, because we can't do C equals A plus B. That's simply not the way the ALU works. So what we actually need to do here is it would need to be A equals B plus C, if anything, because we can see here that B and C go into the ALU, and then we can feed back onto the data bus, and then we can go into A or go into D. A is as good a choice as any, so that's fine for this. So that gives us that part. But I can see now, basically, I'm going to have to rearrange this a little bit. Now also, we want to think about how we want to move these values around. So we still have the same problem that you need to copy a value over before overwriting it, otherwise it's lost forever. That makes perfect sense. So what we could say is, if we did A equals 0 and B equals 1, then another way of writing this would be to come in here and say, let's move C to equal B, and then B to equals A. And I think that should give us the same, effectively the same logic, just in a slightly different order. So the thinking here then is that you'll have the largest number calculated so far in A, then the next largest number in B, and the smallest number in C. So therefore I can see that actually this is probably the wrong way around. Actually, that should be 1, that should be 0. So that means then we start with 1 there and 0 there. The 0 moves to C, the 1 moves down. We do get a 1, the 1 and 1 move down, that gives us 2. The 2 and 1 move down, that gives us that, and so on. So let's actually quickly just test that theory. So if we start here, so our starting position is to have A of 1, a B of 0, and a C of nothing in our first iteration. It will be 0, but we'll just say it's unknown at that point. So after the first iteration going in here, we say C equals B, sets to 0, B equals A, sets to 1 there. We do the addition, and that puts 1 in there. So on the next iteration, we then say C equals B, B equals A. We do the calculation, and I'll put 2 into A. And that should then follow again. So next iteration, C equals B, B equals A, and then A equals B plus C, which gives us 3. So we can see the sequence starting up there, so that's giving us exactly what we want. So I think we have the basis of that now, something that will work for our relay computer. So that is the basic program, I think. Cool, right, there are other considerations we need before moving on to trying to this to assembly. So we've got the registers we need, they're all good. We've used the right registers to get at the LU, so that's all fine. The only thing that strikes me is, of course, because we're using 8-bit registers, we're going to be limited on the maximum value we can calculate. So, of course, out of 8 bits, the most we can go up to is 255. So I guess the question is, where does this sequence go to next? So if we did a calculation of that, so if we're doing 89 plus 144, the total next number will be 233. That's fine. That's still within the limit. So then, if we did 144 plus 233, 377. So we can see at that point then we're bust. We've basically gone over the 255. So what's going to happen there? Because there's no point looping after that, because if we do this addition, we're only going to retain the lower 8 bits of it. Now we could do 16-bit addition, but to do that, we're going to need to be able to store the upper and lower part in either the M register or the XY register. Now, at the moment, the move command doesn't go to those, so we know that's just not possible. So realistically, for the moment, we're going to be stuck with 8 bits. Now, it'd be nice later on to do a 16-bit version of this, but for the moment, there's just nowhere to go with this, so we're just going to have to sit tight and just satisfy that we'll just go up to the 233. Right, so what we really want to do then on this loop is say loop until we're over 255, basically. and that's probably the best we can do, at which point you just want to stop. So how will we know when we're over 255? So let's have a look at the binary representation of these. So let's get our trusty calculator out. And if I look at 233, we can see the binary value for that is 11101001. So that's absolutely fine. If we come in for this next result, 377, we can see then that we're 1 bit over. So if I try and make these line up for you, okay, so if we go like that. So yes, if we do 1011111001. So we can see there that yes, it would set the carry bit, and that's basically because that's the bit you would add to the upper 8 bits of the 16-bit result if you're going to continue on. Now the problem is what would happen is if we did carry on, it would effectively add this to this, and you just start getting nonsense numbers because effectively at this point now we've lost 256 of the value. So really it would be, if we're thinking right, it'd be 377 minus 256, so actually we'd be adding 121 to the previous result. And if we did that, 121 plus 144, you'd actually come out at 265. So you start getting some really weird results, so it's really important that we stop at the point we go over 255, otherwise we're just going to get nonsense numbers. So yeah, the way we can do this is because we know that carry flag will be set, basically if we carry on going until the carry is set, and at that point we just stop. Now it does mean the last value we're putting A will be a nonsense value, but I think we've just got to go with that in this case, just to make this loop work nicely. Now ideally as well, what we'd do is we would copy these values somewhere into memory. So what we could do is every time we get a useful result, we could put it into memory. So we could such say, if carry set, then go to end or something, and then it could be down here. Otherwise, just carry on looping forever again. So what we could say is, if the carry isn't set, then we must have got a good number, and this is where we could actually then copy, say, A into memory. Like so. And what we want to do is then keep moving the address on. So what we could do is put it into an array in memory. So this is actually where the XY register would be good. So you could say put it into memory pointed to by XY, and then increase XY and move it on to the next location. So again, when we've got the ability to store things in memory, this would be quite a nice thing to do, because then what we'll end up doing is writing the results of going along into memory, but as soon as we get a result that then isn't any good and we've blown the 8-bit range, we can then stop at that point. So unfortunately we don't have that at the moment, so we'll just leave it as this. So I think we're now done with the pseudo code. I'm happy that should do the trick. So what we'll do now is convert this into assembly language for the relay computer. So let's take what we've got here and copy that, and we'll get rid of this, and we'll get rid of this. So what we have here now is the Relay Computer IDE. So again, this is available at editor.relaycomputer.co.uk, so you can have a go at this yourselves. And this will basically allow you to do some programming. It'll give you the syntax highlighting. It will help tell you if there's any syntax errors as well. So you'll see that as we go along. Right, well, let's paste this in then. And straight away, we're getting lots of squiggly lines because this is a load of nonsense as far as this is concerned. But that's okay. We can use this as inspiration. So what we'll do is we will stick a semicolon in front of it, and that makes them all into comments, and that gets rid of that for the moment. And we'll use this as our guide. I think I'll just quickly zoom this up a little bit for you as well, so it's a bit easier to see. So what I need to do now basically is convert this into assembly language. So to do that, we'll get rid of the diagram there, and we can look at our railway diagrams here, which will show us the various commands we've got. So we want to set the registers with an immediate value. That should be quite easy to do. We just want to load an immediate value. So our mnemonic is LDI, and then we need a destination, in this case A, and then we're going to set a value of 1. Next up then, we'll do the same to the B register and set that to 0, and that's the first 2 lines of our program complete. So we'll come back to the loop in a second, but let's get some of these moves put in. So again, if we've got register copy here we go, it's the mov instruction. So we're going to move B into C. And then we're going to move A into B. And then we need to do some addition. So then we've got our arithmetic operations here. So we're going to do an add. Now again, we could specifically say that it's going to go to the A register or the D register, and if we don't specify at all, it just goes to A. So that's that done. So that would work for one iteration of the program, but we need to obviously do looping. So this is where we bring in our new branching functions. So first of all, let's get the loop to have another go at this. So we would need to jump unconditionally, but we need somewhere to jump to. So that basically means we need a label. So if we call that again, and what we'll do is we'll pop these over to the right slightly, and then we'll say here is where we'll go again. So we'll say again is here, and this is basically a label. So this basically says when you get here, just jump back to that again line and just carry on as before. So that's doing our perfect do loop here. So the only thing we need then is to stop if we've got the carry flag. So here now we're going to do a conditional branch, and we're going to branch if the carry is set after that add. So BCS, and we'll branch to a label called done. And that can be down here. And now again, we need to do something down here. So you can see I'm getting a squiggle because it says, well, the label needs an opcode after it, or a mnemonic in this case. So in this case, we could just jump straight back to that line. So we could say, well, we'll just jump back to done again, and that will give you an infinite loop. Now, ideally, this is where we should halt. So we'd say, well, when you're done, just halt the computer. But we don't have a halt function yet. That's something we need to implement later on. So for the moment, we'll just keep jumping in an infinite loop, which is a bit dirty, but it'll do. So we should have an equivalent program there now, which is doing exactly the same as what our pseudo code is at the top. So all we can do now is just look for some optimizations. So straight away here, you can see that actually, once the carry flag is set, it's always going to be set unless we do another addition. So what I could do is move the label here instead and get rid of that line down there. So what this will do now is, once it does get to the point where the carry bit's set, it will just keep looping and checking the carry bit again, and it will just basically keep on looping through this section here. So that just saves me an extra, well, in this case, 3 bytes later on, and just is a slight optimization. Again, if you're going to do the halt, you would have to break out to later on the program and then do a halt down there. So another thing I just want to consider here is actually this branching if the carry is set. Now, what would be nicer if we could have a branch if carry isn't set. So what we could do there is say, let's imagine there's an instruction called branch not carry that goes to again. And that will completely get rid of the need to check to see if you want to branch if it's a carry and then jump back to the again. And that will just flow through. But we don't have that. As we know at the moment, we can only check that the carry is set. We can't check that the carry isn't set. So that's an optimization we can't make, but it's worth considering. And the other one as well might be here, actually, could we get away with not having this setting this to 0? We know that when we power the computer on, all the registers will start off being 0. Now, it might be tempting to say, well, let's not have that. But actually, if you do a run of this and then reset the program counter, that B is going to contain some unknown value. So it's very important to make sure you reset these registers that you're going to use to a known value. Never depend on the fact that when you power on, they're going to contain 0, because that might not be the case next time you run the program. So it's always best practice to reset those. Right, so I think we've got our assembly program done. So you see it's quite short, but it should do the trick. Last thing we probably want to do here is just at the top, just let's give it a name. So we'll just say my lovely Fibonacci program, just so we know what it is without having to try and understand the code each time. As well as putting a comment at the top of the program, it's also good practice to explain anything that's not immediately obvious. So you could actually pop in some comments on each line as well. It's the last thing that will be on the line, and of course everything from that point onwards will just be treated as a comment. But we could say here that we want to slide the values and then add together and then keep going until greater than 8 bits or something like that. Not the best comments in the world, but you get the idea. I'll get rid of those though. I think those comments are terrible enough not to bother keeping. But what I am going to do is I'm going to keep some comment lines in here, because now we're about to hand compile this language. Because of course at the moment this is understandable to us, but it means nothing to the computer. What the computer needs is a series of opcodes. So if I drop that away, this is what the computer's after. So again, this is on my blog, relaycomputer.co.uk, and this is where you can find the opcodes for the computer. So what I need to do is convert each of these individual instructions to the opcode equivalent. And that's just a case of just working through them one at a time and just basically encoding them into this 8-bit instruction code. Now, eventually, this IDE will have a feature where it can do this for you. So what I plan to do is add on the right-hand side here a live preview of what the assembled code would look like, and then you can take that and put it into the real computer, or in your cases, if you like to, you can put it into the simulator, which we'll see shortly. But let's have a go at hand assembling for the moment, just to show that actually it's not all that difficult, it's just a tad tedious. So let's start with the first one. So let's sort out these load immediates. So we know that the load immediate needs to start with a 0, 1. We then need the destination, A or B, as this is going to A, which is a 0, and then we need the value, which is that in binary. Next one is set AB to the destination of B, and then we're going to load in 0, which is all the bits 0. So that's the load immediate done. So next we've got the mov instruction, so we know that's an 8-bit move. So let's convert those. So 8-bit moves start with a 0, 0. Then we need a destination, so we're going to C, and then a source is coming from B, and that's that one done. And then the next one, we're going into B, and we're coming from A. And you can see all I'm doing each time is just looking up these parameters just to see what the value should be. Now eventually you'll be able to do M1, M2, X and Y, but at the moment that's not implemented in the Relay computer, so we'll add those later on. Right, we've next up got an ALU instruction. So this starts with a 1000. We're going into A, which is 0, and then we just need the function code for add, which is 001. Right, now we get on to the more interesting ones. So we've now got the branch instructions. So we have a 1, 1. We need to load the J register if we're going to do a jump. And then we're saying we're not interested in sign, we are interested in the carrier flag, and not interested in 0 or not 0. We're also not bothered about copying into the XY register because we're not doing a subrouting. For the unconditional jump, that would be a 1, 1. A 1 to load the J register, no sign, no carry, but we will jump if it's 0 or not 0. In other words, we'll always take a jump. And again, we're not bothered then about the copying the PC to XY there. Now, there's something missing here because we know that a go-to instruction requires 3 bytes to describe it. So we need a value here, and we need a value here. And so for this one needs a value here and a value there. So what is that value though? So this is where these labels come in, because really these labels are referring to a point in the code. But what point is it? Well, to do that, we need to think about where these instructions are going to be loaded to in memory. So what I'll do is I'll load this into the Relay computer starting in memory location 0, but of course you could load this anywhere. But you do have specific, when you're assembling this, you need to tell it where the program's starting, because that's how it's going to work out where all those labels are. I mean, let's work through a quick example of this. So if I start giving these line numbers, so we'll start here, this is line number 0000, so remember it's a 16-bit A address. What I'll do is I'll write these in hexadecimal because that's often more compact way of writing these. So our next location will be 001. This one, even though there's a space here, there's no instruction there, so there's no space taken up in memory, and we can go straight to the next location. So this will be location 2, this will be 3, and the next one will be 4. So you get the idea. So here, this will be 5. I have to be careful now, because the high 8 bits of the target location will go in the next byte. Then the lower 8 bits, so this LLL here, will go in the next location, and then we're on to the next instruction, which is instruction 8. Then we would have the upper 8 bits, and then we'd have the lower 8 bits. And that's where we go to A on there, of course, because that's the 10th location. And then if we have more parts of the program, that'll carry on through B, C, D, E, F, and then we move on to 1, 0, 1, 1, 1, 2, and so on. So we now know that the done label sits at location memory 5, and the again label sits at location in memory location 2. So that means if we want to branch to the again one down here, we go to 0, 0, 0, 0, 0, 0, 0, not sure how many zeros that was, but 8 zeros for the upper 8 bits, and then we need to go to 2 for the lower 8 bits. So 2 in binary is 1, 0. And that'll take us back to the again line. Next, we want to do the done line. So here we're just going back to ourselves. So we're going back to line 5. So again, nothing in the upper 8 bits, but the lower 8 bits need to be 5, which is 1 in the 4, 0 in the 2, and 1 in the 1 column, which would give us a binary of 5. Cool, so that is our hand-assembled program. And now what I'll do as well is, just to make it easier when we're viewing it in the simulator, I'll convert each of these opcodes to hex. So let's have a go at this, and I'll try not to make a mistake. Or if I do, I'll try and spot it before loading it to the computer. But this will just help that when we load these into the relay simulator, we can see the values that we've loaded in, and we can just basically just check that our program is what we thought it was and do any debugging. So let's have a go at this first one. So we have 1 in the 4 column. For the first thing. So all I'm doing here is looking at the first 4 bits and then just working out what the hex digit is for that. So in this case is 1 in the 4 column, so that's a value of 4. In the next 4 columns we have a value of 1, so that is an opcode of 4, 1 in hex. Next up we have 4 and 2, which is 6, and then 0, so that's a 60. We then have a 1 and a 1, a 0 and a 8. We have an 8 and a 1. Next one is 1 away from 15, so that will be E. Then a 8, 0, 0, that we definitely know to be 5. Then we have again an E and a 6. And then 0, 0, and then 0 and a 2. So they should all be the correct opcodes now. Right, so let's get this loaded into the relay simulator. So what I'll do is I will move this over to the slide slightly. Let's just keep enough of it visible. So what we're going to do here is just load this program in exactly the way it would be loaded into the computer itself. So what I'll do is I'll just to make this a little bit easier to see, I'll zoom this in. Yeah, there we go. That'll do. And basically, this is an exact replica of my my real relay computer. So again, you can get to this at simulator.relaycomputer.co.uk if you want to have a go yourself. And basically, what I'll do is now load these opcodes in. So just as with the real computer, it's just a case of setting the opcode and then depositing a next. And you can see down here then the program counter moves on to the next location in memory. And then I'll just quickly pop the switches for the next instruction and deposit next. We'll then go for the next one. And then we just keep on repeating. Now eventually I'll have a nice quicker way of loading values into the relay computer, because for a very, very long program this would be really, really annoying. So I do have a trick up my sleeve for later to be able to read a printed tape or something along those lines, basically to make it much easier to load values into the computer. But for now, hand cranking is the only way we can do this. So let's do that, and then we want a 1, 1, 1, 2 ones there, deposit, then some zeros. Now what I'm doing, I'm going to intentionally make a mistake here, so I'm supposed to put all the zeros in here, but let's say I forgot, because I'm going to show you how you can correct a value. And then the last value we're going to want is a 1, 0 down there. So if I scroll over to the right here, we have a display that shows us what the hex codes are. And if I squeeze this over slightly, we're looking for a 4, 1, 60, 11, 08, 81, E8, 00, 05, E6, oops, 06, and then an 02. And that should be 0 there, we know that's wrong. So what we can do here is, let's see if I make this a little bit bigger again. And we'll go for this thing. So you might need to get a bit close to your screen to see this going on. But I know I need to alter this value here. I also know from my chart here that location 9 is where I need to change that. So what I can do is I can manually update the program counter to point it to that position. And what's happening at the moment is the bit highlighted in orange here is where the program counter is currently pointing to. And you can see down here basically on the program counter the LED is showing you the value. So I know I need to go to position 9, so that should be an 8 and a 1. And then if I load address, you can see now that set the program counter to that value, and we're now hovering over this instruction. And what I want to do is set that value to 0. So I could just deposit a next if I want to deposit and then move the program counter on, or I could just do a straight deposit and that'll just update the value. And this is exactly the same for the real relay computer. If you want to edit values or you want to debug the program and change a value, you could look at your original assembly over here, make some changes, and then just push those changes through to the computer. So you could do things like that, so that would be an easier way to do it. Right, okay, so what we'll do is I will leave the assembly visible just over there. But what we need to do now is actually give this program a try and step through it. So just with the real computer, we need to load 0 back into the program counter so it's pointed to the first instruction. What we'll do is we'll prime the sequencer. And what we'll do now is we'll clock through the instructions one at a time. So if I now step through, we can see that it's picked up the first instruction, which is a set AB, which is exactly what we expected. And if we clock through this, we're expecting to see that the register A is loaded with the value of 1, which it is just down there. So good, that's our first instruction as we wanted. Next instruction then is another set AB. This time though we're going to load the value of 0 into B, which again seems a bit pointless for the moment, but that'll come in useful if we run it again. It will just ensure that register B is set to nothing. Okay, so we're now into the realms of our loop, so we're now down over here and we want to do a move from B to C. So that's the opcode coming up here, and we can clock step through that. And there we go, that's done. Nothing much to see at the moment. Then we're going to move A to B, which you can see down there, that's now taken place, so B now contains 1 as well. And then we're into the LU operation. So we can see that's been loaded up there. We can see it's now performing the AND, so the result now has gone back into register A, and 1 plus 0 is 1. And then we've got to the point of the first go-to instruction. So now we're considering whether the carry's been set or not. So we can see from last LU the carry hasn't been set. So what should happen here is it will load the 0 into the J1 register. It will load the 5 into the J2 register down here. So we've now got the location we will jump to if the value is set, but it's not. So what will happen is we'll carry on and we'll get to the end of the go-to and we'll see we've selected the value onto the address bus, which is there, so that's where we could jump to, but we're not loading the program counter and therefore we're not taking the jump. So if we carry on a step further, we're then into the next go-to instruction. Now the next go-to instruction is the one down here where we're going to jump again regardless. So if we step through that, again we load the 0 into the J1 register, we load the O2 into the J2 register, and we get to the point of taking the jump, which is there, and you can see that we selected the J and it did load the PC, and if we look at the program counter down there now, it's gone back to 2, which we can see up here in orange that it's gone right back to that instruction on the move B to C. So we can step through that very quickly. There's our move. Here comes our add. And by the end of it now, you can now see that we've got 2 in the A register, 1 in B, 1 in C, and 1 and 1 plus 1 equals 2. I think we'll let the computer take over now. So what we can do now is watch it going through the go-to instruction. You can see the carry bit's not set, so it'll carry on. And now it's going to jump regardless back to line 2. And there it goes. So now it'll do the next bit of addition. So now you'll see this value from here pop down to here. So now we have 2 plus 1, and now we get the result of 3 there. And then we go back into our loops again. And now what I can do is I can speed this up now. So what we'd expect this to do is keep on going to the point we get to the carry. Now what I'm going to do is I'm going to quickly jump forward here, and what I'll do is I'll pause it just before it's about to get to that point, so we can just step that through. Okay, right, so we're back. So I've paused this now just as it's going into the add instruction, so it's not quite completed it yet. We're just at step 4 of this instruction, so it's loaded the instruction code, it's just about to take the add. And what we'll do now is, if I look at the B and C register here, I think we've got 233 in that first register. So let's get the calculator up. So I think that's 233. So here we're looking at 11101001. So that's true. I've got 233 in that register, and I think I've got 144 in the other register. So we go 1001 and then all the zeros. So what I expect to happen here is we've got 233 plus 144. We're looking for a result of 377. And as we can see here this time is we'll get actually a result in register A of 0, 1, 1, 1, 1, 0, 0, 1, and there'll be a carry bit there. So let's see if I'm right. So I'll just put that down the side, and we'll just step through this a little bit further. So there we go, it's done the calculations. So if we just bring this back over here again, you can now see we've got the 0, 4 ones, 0, 0, 1. So now actually that isn't 377, it's 377 minus 256. So it's actually 121, 0, 1, 1, 1, 1, 0, 0, 1. So this is now where actually this value is meaningless now. It's the lower 8 bits of what should be a 16-bit result. And what we've done is we carried the 1 bit over here. So what should happen now is we should go into the loop over here, and this time we will take the jump because now the carry flag's set. So let's try that. So if we go through, we come into the goto, we load the 0 into J1, we load the 5 into J2, and now the key thing is now, are we going to take that jump or not? Well, the C bit's set, so there we go, we selected J, we loaded the program counter, and now the program counter's gone back to line 5, as we can see up here. And this now means we're in an endless loop. So if I run this, we're just going to keep on going. Even if I go at high speed, you can see there we're just looping through the same line. So that's it. So the program works as we expected. So if I wanted to start this going again, what I need to do is, the best way to do this is to advance the program counter onto, advance the sequencer onto the first stage, which that'll do there, fine. And then if we clear down the program counter to point back to position 0 again, then what we can do is just set the program going. And we should see then that'll start counting through. So here's the program at full pelt. And you can see it basically going through the adding, moving the values down, adding, moving the values down, adding, moving the values down. So if we go for maximum, so the most my computer can do, you can see it basically going for the full program. And there we go, it gets stuck at the end, and that's where it gets stuck on the carry. So that's it. That is that's a program from Pseudo Code through to assembly language, through to hand assembling into machine code, and then entering that machine code into the simulator and running it. So in my next video, I'll give a tour of the relay computer and just show you around, and then in my final video in this series, I'll actually run the program you've seen here on the real computer. And then we'll take a look at what's next for the relay computer after this. Right, so if you've been watching all the way through to the end, thank you very much, and yeah, see you on the next video.